Real exam questions. This is question 58 about slab design and punching. Which column cross-section do you prefer as a designer if your choice is only determined by the punching resistance of the overlaying slab with an effective depth of 250 millimeters? The columns are in the center of the slab. Rank your choice in descending order. First choice is the best resistance to punching. So as a designer, you can choose between 4 cases. Which of them is the best concerning the punching resistance? First start with column A. It's a diameter of 600 millimeter. The design value of the imposed shear stress is given by this formula. It is the total shear force divided by the critical surface. B is 250, so and B beta is 1.15 because the support is at the middle of a slab, so beta is 1.15. Now we go for mu A, the critical circumference. It's at the distance 2d, so this is the critical circumference. So mu A is of course just the total length of this circle with a diameter of 600 plus 4d. Gives you 5,027 millimeters. So the total resisting force against shear, or the total possible load on the column, is then equal to just this formula turned around, and you got 1.445 10 to the 6th VED. We continue with case B, which is a rectangular of 500 millimeter. The design value of the imposed shear stress is then equal to beta times total force divided by the critical surface. D is 250 millimeters, beta 1.15 for the column in the middle of the slab. The critical circumference is at position 2D from the column. We got that 4 times in the 4 corners, so that the total critical circumference is of course 4 times 500 plus a full circle with radius 2d. Gives you 5,242 millimeters. And the total reaction force that you can take up with a design shear stress of VED is then equals to 1.478 10 to the 6th VED. Then we look at the case C, which is a rectangular 350 by 600. Design value of imposed shear stress is equal to this. D is 250, beta 1.15. The critical circumference is, of course, in the 4 corners, the circumference of a circle with radius 2d plus 2 times 600 and 2 times 350. So we arrive at 5,042 millimeters, and the total resistance is then equal to 1.45 10 to the 6th VED. Then we have the condition, the case of a cross-section D, like it is stated here. The design value of imposed shear stress is equal to this. D is 250, beta 1.15. Now the circumference, critical circumference, is on a distance 2d. So we start with here between those 2 points, it's at 2d. This between those 2 points, it's also at 2d. The same happens here. So this is one portion that I can draw immediately there and there. And from this point to this point, it's a part of a circle. But because you're turning around 360 degrees, all those 4 parts together makes the circumference of a complete circle. So what we need now is this distance, which is of course equal to 430 millimeters. So mu d is then equal to 5,102 millimeters. And the total force that can be taken is then equal to 1.467 10 to the 6th VED. Now, to sum it up, this is the we can order those cross sections in the sense of that B gives you the largest number here. So B is first, then D, then C, and then A. I've done it now with VED, which is the maximum load on the column. But of course, you can look directly at the first critical circumference. It's the same, but we should now be careful because there's also a limiting value on VED, which is proportional to the circumference of the cross section of the column. So sometimes this can be more limiting than the first critical section. So that's why I checked here also the circumference of the column cross section, and you see that this is also following the order B, D, C, A.